So let's get this presentation with a humble title started. Actually, this is a wordplay. This is a homophone wordplay, but according to the feedback that I received, it was not so successful because I think that nobody got it. It's a wordplay with a verse of a popular song of a heavy metal group, but yeah. So if I remember, I'll tell you the song at the end of the presentation. So the purpose of this presentation is mainly reporting back on what has been done during the last months on the BFQ IO scheduler. And then I'll show you a demo just to give you an example of what BFQ can do now. The nice thing is that this demo is finally with the MMC subsystem supporting blk-mq. So for the first time, we have tests with blk-mq and eMMC. And then I will finish by sharing with you what I would like to do as next steps. So as you have seen, this presentation is about an IO scheduler, so just to make sure that we are all on the same page, and just spend a few words about IO scheduler in case someone doesn't know them very well. So these IO schedulers are components that decide the order in which IO requests are to be served by a given storage device. In particular, they do this job in case there are several processes competing for the same storage device. And in that case, it's about the same role as a traffic policeman on a crossroads. So this job is rather important. Why? Because it is necessary to achieve several relevant goals. One of these goals is reaching a high I/O throughput. You need to control the service order of requests because storage devices the throughput of storage devices is very sensitive with respect to the service order of I/O requests. Another important goal is guaranteeing a low latency to the tasks that, to be accomplished, need I/O. For example, reading the frames of a video. An important class of tasks are interactive tasks. For example, starting an application, reading a file, and so on. In this case, if you guarantee a low latency to interactive tasks in a system, then you are guaranteeing a high responsiveness to applications, to services, to whatever in that system. In the typical terminology of the mobile computing, this is called guaranteeing, they say guaranteeing a low lag. The equivalent of guaranteeing a high responsiveness is guaranteeing a low lag, and that's other terminology. What else? In my work on BFQ, and I'll do the same in this presentation, I have used as a reference for responsiveness the startup time of applications. So, starting an application is evidently an important example of an interactive task. Measuring the startup time of an application is evidently a good measure of responsiveness, and it also gives us an idea of the latency that we can guarantee to any possible generic interactive task. Okay, these schedulers have also other goals, but this is out of scope for this presentation. Finally, where are these components in Linux? They are in the IO stack. The IO stack now comes in two flavors, the legacy block layer, BLK, and the new multi-queue block layer, blk-mq. The sets of schedulers available in the two versions of the block layer differ. In particular, BFQ is not available in the legacy block layer. You can have it only out of 3. While, fortunately, it has been added into the new blk-mq. Okay, so, first part of this presentation, what has been done, we have improved BFQ. We have made it faster and made it more effective. effective in terms of guaranteeing low latency and at the same time guaranteeing a high throughput, and I'll tell you some details later. How much work? The effort has been, I tried to evaluate it around 18 person months, spread over 12 people, me plus 11 students. Each of them has really worked on this and has authored or at least signed at least one of the contributions that are now publicly available. What are these contributions? As for the kernel, 37 new commits, and 5 of these authored and 14 signed by people in this task force and all the rest by me. Okay, and then really a ton of commits for the development branch of BFQ, which is the branch where we do the actual work. Then from that branch we pick the commits to submit for mainline. Also in this case, 16 of these commits authored by several good young students. But we already have additional commits. 14 commits are under test, so we just need to finish testing them, and then they are ready to be submitted. And I already have further 18 patches that I sketched or designed, and start to work on them when it is time to. Finally, we are at a good point in improving the interface of C groups for the I/O controller, because there is a problem there. The I/O controller provides the so-called proportional share policy. You can assign weights to every group, to any group, and the group will receive a fraction of the throughput proportional to its weight. But it doesn't work because it works only with CFQ. It's wired around the CFQ I/O scheduler. Yeah, so this is a problem. We are unifying the interface in such a way that you can seamlessly activate the proportional share policy, whatever the underlying scheduler is. And this is actually providing other benefits for the interface, but we will see when we are ready and we will submit the commits changing the interface. Okay, we also contributed to the benchmarking area. In the benchmarking area, we are now at the third version of a new test for the Phoronix benchmark suite. It's a responsiveness test, but now we have the same test also in the MMtest suite. This is basically because of your feedback. The feedback you gave me about the Phoronix suite that rang some bells, and I decided to look for other suites, other people that had somehow more credit. Yeah. Okay. Fortunately, we made it, and we are just finalizing the post-processing of the results. But they already tried the test, and they did like the results. I guess you were in CC. Anyway. Then these tests live in the S benchmark suite, which is the main suite that I'm using for testing. And also for this base suite, we have now a new, rather interesting feature. It can now replay the I/O of an application, because to measure responsiveness, we measure the startup time of applications, but in some cases it's hard to automatically start certain applications, especially X applications. So with this new feature, it can replay the I/O of that application without actually starting the application. This can be rather helpful on systems where it is tricky to have those applications running. Okay, and then in general, really a lot of commits improving the suite, basically to make it help Linus surviving. Okay, what did we improve with all these contributions? Well, we improved efficiency. We made BFQ faster, and here are some examples. BFQ is an accurate I/O scheduler, so it has to make non-trivial decisions when it is time to decide the service order. This implies that it has to take several steps, which means that it takes time. So we shortened this time, and by doing so, we increased the number of IOPS that can be processed when you have BFQ as a scheduler. For example, on an Intel i7, we are now at around 400 kilo IOPS. And on the processor of the high keyboard, we reached 80 kilo IOPS from 30. So,
I have a question.
Yeah.
I should have two questions.
Yeah.
I have two
And
questions.
2 microphones. One per question.
So I have two questions, if I may. Can you explain the word sustainable here? I'm
Yeah.
not sure that I get that part.
Yes. It's just that to serve your requests at a given speed, you must execute all the code needed to process each of those requests in time. Okay? Requests just don't flow from processes to device. They are processed in the I/O stack. And the I/O stack must be fast enough to comply with the rate at which you want to serve the requests. Every single request must be processed. So you can sustain a certain number of IOPS if you are fast enough in processing requests.
Okay, I think I misread the word sustainable, because there's another semantic with sustainable that says that sustainable can be carried like environmentally sustainable.
Yeah,
So I might
no.
have misconstrued this.
Yeah, no, sustain,
Yeah, so hence the confusion.
yeah,
It's
yeah,
on my
probably
side.
it's a wrong word, yeah.
No, it's on my side.
Maybe I found it used. Yeah, it's just that you don't go faster than 400 kilo IOPS. If you attach the, for example, null block module, yeah, you know that? Yeah, and that's the maximum speed you reach, just because the CPU is the bottleneck. Yeah. Okay.
The other question I had,
Yeah,
sorry. Can you explain the difference between, like, there's a huge improvement on Intel and like a good
Yeah.
improvement on ARM as well, but is there any reason for that?
Yeah,
Like
there
the
is-
ratios isn't
yeah,
exactly the same.
There is, it's just because we didn't have accurate measures for the Intel. So 50 were just conservative. So that is a mixture of actual improvement and improvement in the measurement, because believe me, it's not that easy to measure the number of IOPS. We had to write a dedicated test. Also this, I didn't add it, we also made that what's called speed test, IO speed something, made by another student of mine. And yes, it allows you to measure that. Now, using that script, we could precisely measure what the actual. So I don't really know how it was before, but for sure now I can prove that it's 400. Yeah, that's the reason, yeah. Then we improved also the throughput that can be achieved by BFQ. This is by improving the service order of request in a particular case. We had problem in this particular case, random I/O on flash storage without internal queue, which means the storage of the keyboard. And yeah, we solved this problem, and now we went from 7 megabytes per second to more than 15 megabytes per second, which is the peak rate. As for responsiveness, we removed several nasty outliers. They were, occasional, but they were very nasty. And so, for example, with LibreOffice Writer and some heavy workloads in the background, on certain devices like that Blaster SSD, occasionally LibreOffice Writer took like 45 seconds to start, which is, infinite. And we solved the problem, and now the time is just 1 second. Against about 14 seconds with any of the other I/O schedulers. We had another outlier that somehow was triggered on that other SSD, and it more than doubled the startup time. We removed that too, and now we are around 3 seconds against 20 seconds with the other scheduler. And other cases, but I don't want to bore you because this is the end of numbers, so for those of you who survived to this burst of boring numbers, you have a reward, which is this demo, which probably is a little bit less boring than all these numbers, and some graphs, but they are on some extra slides. I will show them only on demand. I guess there won't be such a demand, so I want just to credit Linus for running the test from which basically all these results have been obtained. So the demo is with the high key, and the application, it's a key with Debian, and the kernel 4.16, it was the release candidate to the most recent release when I did this test, as shown there in the video. The application for which I measured the startup time was Xterm. Actually replayed I/O for Xterm because I had problem with the Xserver with that release candidate. And so we will start Xterm first without any I/O in the background, okay, just to see how long it takes. And then we will repeat this test with some I/O in the background. So to start, this is one of the scripts in the S benchmark suite. So we repeat this twice with no background workload, and the startup time should be around 0.3 seconds. Of course, we call caches because we want actual I/O. Now we repeat this, but we will put in the background one file read and one file write, so basically a file copy, known as I/O scheduler, but the results that you are about to see are the same with any of the other schedulers. We will do this only once, so one reader, one writer, sequential, and you are about to discover why we are doing this only once, because you can go take a coffee, because just one start. Why? Because the I/O in the background is sequential and greedy, which is the perfect I/O to get the peak rate. For this reason, this is the I/O that both the I/O stack and the logic inside the device do love. They love this type of I/O because it gives you the peak rate, so they privilege this I/O with respect to the mostly random I/O to start Xterm. That's why Xterm stops. Yeah, I have to invent something else to say because, yeah, no, it's almost done. And yes, and this is what you get. A lot of, I mean, infinite. Now we repeat this test, but with a much heavier workload, 5 readers and 5 writers, but this time we will let BFQ handle the I/O. And we will repeat this a few times to check variability. 3 times, 5 readers, 5 writers, but this time BFQ is I/O scheduler. And on average it should be 0.8 something. So yeah, these are the this is the current performance of BFQ now, that you can find now. Oh, okay. So, yeah.
Because it isn't completely obvious that having 5 readers and 5 writers is a case that is worse than having 1 reader and 1 writer.
Yeah.
But
it's just, I mean, experimentally, I've seen that it's killer workload.
So if you did this, the 5 readers, 5 writers, and another scheduler, it would take even longer than the.
Yes, basically it will go on forever. Okay. It goes on forever. Yeah. There is a reason for that, but I don't get that. Okay, so BFQ seems to be much better than those other schedulers in terms of responsiveness, and I didn't show it, but believe me, I have those extra slides. It's about the same in terms of truth, so it has about the same performance as the other scheduler in terms of truth. So in the end, it's much better. Still, it is not the default I/O scheduler. The default is deadline. This makes sense on very fast devices because deadline is very lightweight. I mean, it does almost nothing. So it's rather fast to do nothing. So the sustainable throughput in that case is higher. But there are also devices that are not super fast, like all single queue storage. So for single queue storage, BFQ does seem a much better option, according to all the tests run so far. So the idea is to propose it as the new default I/O scheduler, but we are still waiting. I'm still waiting for a few more test results, faster storage, faster flash-based storage, and then some third-party tests just to have better ground, to propose this. So this is the near future. As for the midterm, these are the challenges that I have in mind. The purpose of the last year of work was to make BFQ become much faster and much more effective. Actually, as I showed you, we seem to have succeeded. But this is not yet enough if we want to move to a different context, that is the enterprise context. Because in that case, enterprise storage is even faster and even more sensitive to the order of the I/O requests. Because storage, this enterprise storage is more parallel and it has multiple queues. So we have the same two barriers as before, as this last year, efficiency and effectiveness. But now they are just much higher, because we need, I think, at least 1 million IOPS to comply with very fast storage, order of magnitude. And as for effectiveness, the barrier is high and tough because this highly parallel storage is very sensitive to the state of the input queues. It needs all the queues to be constantly non-empty to reach the peak rate. But if you keep these queues non-empty, then the device has several requests to choose from, to choose what is the next request to serve. And it does change the order of the service of this request with respect to the order in which you dispatch the request. In case it thinks that it's better to change it, it does change it. So now, the challenge is rather hard. How can you still guarantee a low latency to tasks? You need to control I/O to guarantee a low latency. How can you still guarantee a low latency and at the same time keep those queues non-empty? Well, and by doing so you lose control on the I/O. Okay, this is the challenge, and this is what I would like to face in case Dinaro will be happy to support the continuation of this work. And this is all I wanted to show.
Isn't this the reason why people invented open channel SSD? That they have no control over the I/O scheduling in the device, so they just get open channel instead, and then they can control it.
Yeah.
So we would be able to use our algorithms on open channel SSDs and get like a nice control data flow.
That's an option.
So I don't know if the future belongs to open channel actually, and this free-thinking devices go away because the operating system simply can't deal with them.
Yeah.
But the industry will decide, of course.
Yes. Yeah. Probably. Yes. Can you? Go on.
It sounds like what we need is for all those enterprise SSDs to implement the same kind of delay control that we have in network hardware, where we have multiple queues. We're hitting some of the same problems. The operating system can schedule packets going to the network, and it does so very efficiently nowadays in fairly recent kernels. But then when there's multiple queues in the network card still has to make sure that it treats all queues in the right way, that you get the maximum throughput, but you also get no big delays on any of them. And this seems that there's absolutely no difference to what the storage does here.
Yeah, the problem is that in case of network, the throughput is not that sensitive with respect to the order in which packets are transmitted. So it's
correct.
But anyway, I tried to make this a little bit more dramatic, but I already have a prototype which seems to work. I had found a trick. Yeah, but I can tell you before Linaro.
That's a trick to work around devices that do not behave as they should, correct?
I mean, they behave, how can I say? They have a right to change the order of their request. That's how they work. They have black boxes, and they don't promise that they will respect them.
They behave in a way that matches the specification, but it is not a way that guarantees the lowest latency and being better than the competition.
No. Absolutely no, because the main goal is throughput.
No, it's not. These enterprise storage arrays are extremely sensitive to latency, and that is the absolute goal. It's just that some people mess up the implementation of it because.
Oh yeah.
But they all try to have the extreme low latency on a single.
Yeah, but it's a different type of latency. Yeah, this is about task. This is what matters for a user or for a client. It's the latency advertised is sort of higher level.
I have the response to my question actually.
Ah, okay, great.
I want to know the improvement of the BFQ. How do we reduce the latency and increase the output?
Okay, I'll try to tell this very briefly. The idea is as follows. BFQ serves one process at a time. Okay, it gives a time slot to every. It's actually a budget. But let's say this is just time. So there is one slot for each process. During that slot, BFQ guarantees to that process that only that process will be served. So if that process is not fast enough to, to feed the device and keep the queues of the device full, or at least non-empty, it will just happen that that process remains without I/O requests in some time intervals, because the device is very fast. And the device will remain without requests too. In these holes, that's where you lose throughput. So what I made is a prototype that during those holes just injects some requests from other processes in a controlled way. Believe me, the throughput goes up immediately. It's rather impressive because I tried to switch it on and off. The throughput goes up, but the process in service is not affected because I have a simple feedback loop. At every slot, I try to inject a little bit more until, by just checking, this causes the throughput of that process to go down. So if I am injecting too much, I reduce the amount of injection. If I can inject more, I go on. It's a feedback loop. It's not stable, but when you look at throughput, you never look at it like in a time window of 20 microseconds. You look at throughput like in at least 100 milliseconds, which is an epoch. And so it seems to work. Yeah, that's how I'm trying to, Just a prototype for the moment.
So one more thing, boot up, have you measured, how much it might improve? Because on embedded devices, what we have seen is during boot, the boot time is somewhat important. And there's a lot of I/O generated.
Yes.
I'm wondering if you have any.
I have a very short answer to that because basically Jens Axbo solved this problem for me. Because it's now impossible to have BFQ at boot. So ask him. Yes, there are some improvements in BFQ, and they did improve the boot time, but then it was decided that you have only deadline at boot, and you can have BFQ only through you have rules or by setting it manually. So you, yeah.
But once it becomes the default, then
Yes.
No, I mean, if you have seen improvements, we can make the customization. The ARM vendors can make that, but I'm just curious if you have seen any improvement.
I mean, it's not faster than the other schedulers. I managed to have it as fast as them just because the only thing that you need to do during boot is just to pass every request as fast as possible. You don't need any special control because you have a certain amount of I/O to do, and you are done when all that I/O is finished. So you have just to give this I/O as fast as possible to the device. You have improvements on rotational devices, but this is not. I mean, yeah. For I mean, flash storage, what just matters just you give I/O as fast as possible. Yeah. Yeah. Is there microphones?
Was it ACDC?
Yeah, great, yeah, exactly, yeah, it was TNT.
That was a question?
Wow.
Of course.
Okay, no, because I asked somebody else and they said, oh.
I don't know, I thought right away.
Great. Wow. Okay, thank you.